couldn't find number 4. And this is under the topic, right? This is under the topic of what I call the function analysis. Now, function analysis oftentimes come in 2 different forms. One is that they give you a graph. Okay, so I actually work one out for the next problem, which is under that particular form. This particular form gives you a chart. Okay, so it gives you a chart, and then let me just go ahead and draw that out, just so that we have something to refer back to, and just quickly do that. And the chart here, f of x, f prime of x, and double prime of x, -1, 4, -2. This one this is negative, positive, negative, 0, 0, 0, positive, 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 2. Positive. Okay. So let's read this together. Function f is continuous on the interval from 0 to 4. From 0 to 4 is a continuous function. It includes, now look at this, is a closed interval 0, open interval at 4, meaning it includes 0 and it does not include 4. You want to even just say it in your mind, say that when you read this problem, just so that at least that piece of information is registered in your head in case you need to use that information. I don't know, I have no idea whether you will need it or not, but make sure you don't miss small details. Now here it says the function is twice differentiable. Twice differentiable simply means that you can take the derivative twice, right? First derivative, second derivative. That's what it means. Okay, so don't get too worried if it gives you a term that you may not quite understand. All right? Except at x equal to 2. Now at x equal to 2, notice that you don't have a value for the first derivative and you don't have a value for the second derivative. Okay? Where den indicates that the derivative of f do not exist, right? Do not exist. D and E do not exist. Okay? At x equal to 2. Alright, part A. We're ready to do this problem. For 0 to 4, find all values of x at which f has a relative extrema. Relative extrema, remember extrema simply means is either a maximum or minimum. Extrema. Minimum, maximum. Hopefully you can connect that term and remember that term. Extrema, extreme. So it's either maximum or either min. And it's relative maximum, relative minimum. Now, if it's a global max, global min, that can still be part of the relative maximum minimum. But what this means is, and let's keep reading, determine whether f has a relative max or min for each of these values. Okay? Because not only do you need to say, oh, these values are going to give you extrema, you need to know, you need to be able to say, oh, is it the maximum or is it the minimum? And you need to justify your answer. Okay. Every time you hear these words, extrema, minimum, maximum, you think of what concept? First derivative test. That's right. And this is the first derivative test on f. Now, I also make that emphasis on, I punctuate that word and say f. The reason why I say that is because sometimes they ask you for f, what they give you is g. Right? Give you something totally different. Sometimes they give you f and they ask for g. In this case, we are safe. Asking for f, they give us f. We're okay. So now we're looking at first derivative test. So let's do part A, right? Part A, we're talking about first derivative test. And first derivative test simply means that we set f prime equal to 0. We say at f prime, where do we get 0, right? F prime equals 0. We get what the values. Well, then that means we need to go to f prime. We say at f prime, where do we get 0 or undefined? 1 and 2, that's right. So we can sketch this out. We got 0 and 2, and this is the x value, and this is f prime value. And we at 1 and 2, right? X equal to 1 and x equal to 2. X equal to 1, f prime is equal to 0. X equal to 2, f prime is not defined, right? Do not exist. So that means f prime right here is 0 and x equal to 2 is undefined, right? Even though they use the notation d and e, but we know in our own way we say it's undefined. So let's take a look at this. Very simple. Anything less than 1, right? 1 right here, less than 1. I'm still looking at f prime because it's the first derivative test. Anything over here is a positive or negative? Positive. Positive, because it says that, right? Positive. Positive. Between 1 and 2, what do we have?
Positive.
Still positive. Good. And then 2 and on, we get negative and negative and negative. Right? We have to double check, right? Everything is negative. So that means we're going to have something like that. Okay. Now, if we look at this, it seems like we have a graph that goes up like this and somehow flattens out, but continue to go on after 1. But at some point, there is no derivative, so that means it's going to go up like this and then go down like that. Right? Now, it can be two scenarios. It is possible that you can have asymptote where it goes up like this and then it goes down like that. Or it could be a cusp, right? Goes up and sharp turn, right? We don't know, but at least based on this graph, we can say, well, at least at x equal to 2, we have the relative maximum. Does that make sense? So that's our answer for part A. That's our answer for part A. Now part B says, well, on an axis provided, sketch the graph of the function that has all the characteristics of the f. So somehow I had to sketch a graph based on what I have here and based on what I have over there. Not so easy, isn't it? But that's okay. In order to find out, in order to sketch the graph, I also need to know the concavity of the graph, right? Not only do I know the rise and fall of the graph, which is first derivative, I also need to know the concavity of the graph, which has to do with the second derivative. So take a look at the second derivative test. We still, the critical point is, so f double prime equal to 0, we end up with x equal to 1 again. X equal to 1, we get 0 for double derivative, and x equal to 2, we get a no double derivative, and we also get 3, right? Because this double derivative is equal to 0. Make sense? You see, first derivative test at x equals 3 didn't show up. But for second derivative test, x equals 3 shows up. Because the second derivative is equal to 0. So if I sketch this out, I get 0, 2, and 3. This is x, and this is double derivative. At x equal to 0, we got 0. X equal to 2, we got undefined. And x equal to 3, we got 0. And let's take a look at the section. Less than 0, we got negative double derivative, so concave down. Between 0 and 2, we got positive, so we got concave up. Between 2 and 3, we got negative, so concave down. And 3 and on, all the way to 4 at least, because 4 is our ending point, we got positive, so we got concave up. So now we're ready to sketch it. We need to sketch this graph, and this graph, let's start with the max and min, 1 and 2. So 1, so 0, 1, and 2. And later on I'm going to have a 3 anyway, but start with this. And then our ending point is from 0 to 4. So 0 to 4, this is our domain from 0 to 4, so I don't really need to work on this portion. And that's the axis that was provided for us. So from 0 to 1, we're going to have a rise and fall. Now, actually, before we do that, we also need to take advantage of this. Right? We actually got some real points going for us. We got, when x is equal to 0, f of x is equal to -1. So we say, okay, now the first point is right down here. First point is right here. This is our first point. Right? 0 and -1. At x equal to 1, we got 0. So it's right here. At x equal to 2, we got 2. Right? At x equal to 3, we got 0 again. And at x equal to 4, we got nothing. We don't because it doesn't include x equal to 4. Okay, so now let's take a look at the rise and fall. It rises all the way to 1. Makes sense? It rises all the way to 1. All the way to 1. And then from 1 to 2, continue to rise. And from 2 and on, it continues to fall until we hit 4. Right? So that makes sense. It goes up and down. Let's look at the concavity. From 0 and back, I suppose we only have to worry about this portion. This is what's going on here. This is supposed to be 1?
Yeah.
Oh, okay, I made a mistake. This is supposed to be 1 right here. 1 right here. Makes sense. Like 1, 2, 0. So make that correction here. This should be 1. Okay. Now, take a look at this. 0 and from 0 to 1, you got negative concavity, so concave down. So here, look at this. You got a concave down. So the graph going here. So there's that part. From 1 to 2, you get concave up. So concave up. So you can exaggerate this, not a problem. Okay, so concave up like that. So, and then 2 to 3, you get concave down. So 2 to 3, you get concave down like this. Oh, now notice, that's the reason, right? This is the cups. That's the reason why you didn't have a derivative in the first place. Yeah? Makes sense. That makes sense. And then from 3 to 4, you get concave up. So you're going to go like that. Okay? So you can go like that. Now, of course, at the end, you're going to put an open circle right here because it does not include x equal to 4. There you have it. That's the graph. That's part B. Question so far. Does it make sense to you? Notice now we can actually come up with a graph by using the table. Now, but this table was useless until we could turn this table into these meaningful charts. Right? This table wasn't going to be that useful to us unless we can turn that into this, so that we have way to visualize what the graph looks like. Okay, now let's go to part C. Go to part C. Okay, now here it says let G. Okay, well this is very strange. Now remember I said sometimes they give you F and then ask you about G. Here it is. Here it is. G now. They say G of x is equal to integral from 1 to x f of t dt. Now simply it just means, now every time you see something like this means this, okay? The way we define G is the definite integral of f, which means is the area under the curve of f from 1 to some distance along the x-axis. So what that means is this, is that the way we define G basically is the area under the curve from 1 to some distance away. Area under the curve. Does that make sense? Okay? And this is for the open interval from 0 to 4. Now, find all the values that G has a relative extrema. Now again, relative extrema means we need to employ first derivative test. But this time they're asking for the extrema for G. That means you do the first derivative test on G. That's right. That's right. So the first derivative test on G. So that means we are setting G prime equal to 0. But G prime, okay, we have to back up a little bit, right? G is integral of f, so G prime is f. That's it. So G prime is just f. Think about it. If the integral of f is g, then the derivative of the integral is g. Right? You gotta be able to do this, okay? This is a very, very important point. You almost always, this will show up on all the problems that involve with function analysis. Let me say it again. That's why the logic, the way I talk through this problem is very important. I want you to model and mimic the way I think through these problems. They ask for extrema of G, so I immediately write first derivative on G. And then when I say first derivative on G, then I write G prime. And then I will go back and look at what G and F have to do with each other. In this case, if G is integral of F, then G prime is then F. Right? So if I said G prime equal to 0, that means I'm setting F equal to 0. Right? Now, so instead of thinking about G prime, you're thinking about F now. Okay? What are the critical points when F, not F prime, but F equal to 0? And 1, and then 3. You see that? It gives x equal to 1 and 3. So now we have 1 and 3. These are the x values. Right? And we're looking at G prime. But remember, we're not looking at G prime because we don't have a chart for G or G prime, but we have a chart for F. So instead, we're looking for F. At x equal to 1, f is equal to 0. Right? Look at this. Right? F. At x equal to 3, f also is equal to 0. Now let's look at what's in between. Anything less than 1, we got negative. We got negative. Boom. Like that. For G. From 1 to 3, between 1 and 3, f is positive, positive, positive. If f is positive, that means G prime is positive, so G will rise. Anything over 3? Anything over 3 for f? For f, we got negative. And so if f is negative, that means g prime is negative, so g prime will fall. G will fall. So take a look at this. Determine where the extremos are. We say at x equal to 1, g has a relative what? Minimum, right? At x equal to 3, g has relative max. This is my answer. This is my justification. And I'm done with this part. And I will get all the points I need. This is very important, okay? This part is critically important, and it relates back to the definition that they set up for you. Tricky, very tricky. Part B, for the function g, find all values of x, which g has a point of inflection. Now, when I say point of inflection, we're talking about concavity, right?
Yeah.
In concavity, we're talking about second derivative, right? So we're talking about second derivative test on g. So we're talking about g double prime. But g double prime means what? F prime, that's it, F prime. And if we want to set g double prime equal to 0, it is the same as setting F prime equal to 0. Now, didn't we do that already?
Yeah.
We set F prime equal to 0 right here. Right? And we figured out that x will be 1 and 2. And look at this, I'm drawing exactly the same thing. Right? 1 and 2, x. And we're talking about g double prime. And remember, g double prime is F prime. And we got 0 for here, undefined for that. And we got positive, positive, and negative. You see, the signs are exactly the same as part A, where you have first derivative test on f, but in this case, first derivative test on f is second derivative test on g. Now, instead of drawing rise, and fall, what do I draw now? Concavity. So this is concave up, concave up, concave down. And the point of inflection is where?
2.
2. X equal to 2. Point of inflection. And here you have it. The change of concavity is your point of inflection, and therefore that's a justification for x equal to 2 as a point of inflection. Again, very important. That's why the language, the way you write a solution is so important. Second derivative test on g is first derivative test on f. And you go to f for this. Yeah.
Why does that write in gx equals integral 1 to x on top, while there's an x in the other one?
If the x is on the other direction, right? Are you talking about if this x is on that side?
I'm talking about why just simply just write gx equals integral fx dx.
Because if you only have the indefinite integral antiderivative, then you will miss out on the integration constant. Right? Remember, every time if we say if we don't have this, the answer is going to be something plus c. And if without plus c, then we won't be able to know the solution.
What does the one mean?
The one that will allow you to situate here, start from here, and give you a definite value. Okay? It will give you a definite value. So it is the equivalent of giving you the value of the function plus c. Right? Makes sense? Okay? Good, good. Any questions on this? Good.